For decades, astronomers believed the earliest stages of the universe would remain incredibly difficult to observe directly. The first stars, the earliest galaxies, and the compact stellar systems that helped shape them were separated from us by billions of light years. Studying them was like trying to reconstruct an ancient civilization from fragments of ruins. Then the James Webb Space Telescope changed the game. With its powerful infrared instruments, Webb can detect extremely faint light that has traveled across billions of years of expanding space. That means astronomers are not simply looking farther away. They are looking further back in time. Among the most fascinating observations are distant compact stellar systems associated with galaxies seen billions of years in the past. One particularly interesting example involves a strongly lensed galaxy sometimes nicknamed the Sparkler Galaxy, where Webb observations revealed numerous compact sources that are consistent with globular cluster candidates. Globular clusters are dense groups of stars bound tightly together by gravity. In the modern universe, many are extremely old, making them valuable records of early star formation. Finding similar systems around a distant galaxy is important because astronomers can observe them at an earlier stage of their history. Instead of studying only ancient clusters that have survived until today, researchers can potentially watch versions of these systems when they were much younger. That gives scientists a new way to investigate one of astronomy's biggest questions: how did the first generations of stars organize themselves into the structures we see today? The answer may not have been as slow or simple as once imagined. Young galaxies were environments filled with gas, radiation, gravity, and rapidly forming stars. Within these chaotic conditions, dense stellar systems could assemble remarkably quickly. Webb's observations provide evidence that compact stellar populations were already associated with galaxies billions of years ago, giving researchers valuable clues about how galaxies accumulated their stars. But there is another reason these observations are possible. Gravity itself can act like a telescope. When a massive galaxy cluster lies between Earth and a distant galaxy, its enormous gravity bends the path of light passing around it. This phenomenon is called gravitational lensing. The result can magnify distant objects that would otherwise be far too faint to study. In some cases, the gravitational field can even produce multiple distorted images of the same distant source. What looks like several objects may actually be different images created by the curvature of spacetime. For astronomers, this is incredibly useful. The natural lens effectively gives Webb additional magnification, allowing researchers to examine structures that would otherwise appear as tiny points of light. And this leads to a much bigger discovery. These observations demonstrate that the early universe was already capable of producing surprisingly organized stellar systems. That does not mean our understanding of cosmic evolution has collapsed. Instead, it means scientists now have new evidence with which to test their models. The early universe may have been more efficient at forming dense stellar systems than previously assumed. Galaxies may have assembled their stars through multiple pathways, including mergers, rapid bursts of star formation, and the collapse of dense gas. Every new observation helps determine which processes were most important. And Webb is only beginning to explore this territory. As astronomers examine more distant galaxies and gravitational lensing fields, they may discover additional compact stellar systems from different stages of cosmic history. Each one becomes another piece of the puzzle. Because when Webb observes a galaxy billions of light years away, it is not simply showing us a distant location. It is showing us a moment that happened billions of years ago. And hidden inside that ancient light may be the story of how the first great structures in the universe began to take shape. The most remarkable thing about James Webb is not simply that it can see distant galaxies. It is that those galaxies preserve information about a universe that no longer exists in the same form. Light travels at a finite speed. So when astronomers observe an object billions of light-years away, they see it as it appeared billions of years ago. Webb has transformed that principle into a powerful scientific tool. Its infrared sensitivity allows researchers to study extremely distant galaxies and compact stellar systems whose light has been stretched toward longer wavelengths by cosmic expansion. Among the most intriguing targets are ancient globular cluster candidates. These compact groups of stars can contain enormous numbers of stars packed into relatively small regions. Their properties can reveal how star formation occurred inside young galaxies. If astronomers can determine when these clusters formed, how massive they were, and how they were distributed around their host galaxies, they can reconstruct important parts of early galactic evolution. And that could answer a long-standing question. Did galaxies build themselves slowly, or could complex structures emerge remarkably quickly? Webb is providing evidence that the answer may involve both processes. Some galaxies appear to have undergone rapid periods of star formation, while others show evidence of interactions and mergers. In these environments, dense pockets of gas could collapse and produce enormous populations of stars. Over time, some of those populations could become gravitationally bound clusters. Eventually, galaxies continued to grow, merge, and reorganize. The compact clusters remained as surviving records of those earlier events. That makes them similar to archaeological artifacts. Except instead of being buried underground, they are buried in ancient light. Gravitational lensing makes these investigations even more powerful. A massive foreground galaxy cluster can distort spacetime and magnify light from objects located far behind it. Astronomers can model this distortion to estimate the locations and properties of extremely distant sources. The technique is not perfect. Lensing models contain uncertainties, and researchers must carefully distinguish genuine objects from lensing artifacts or unrelated background sources. That is why observations are often followed by additional imaging and spectroscopy. Science depends on verification. But when multiple observations support the same interpretation, distant compact sources can become valuable evidence for understanding how early galaxies developed. And the implications extend far beyond globular clusters. The same technology allows Webb to investigate the first generations of galaxies, the growth of massive black holes, the chemistry of ancient stars, and the conditions that existed during the universe's earliest eras. Each observation adds another layer to the cosmic timeline. What once appeared to be a blank period between the Big Bang and the mature universe is becoming increasingly populated with real objects. Galaxies, stars, black holes, dense stellar systems, and enormous structures connected across unimaginable distances. The universe did not suddenly become organized. It evolved through countless physical processes operating across enormous stretches of time. Webb is allowing scientists to see some of those processes closer to their beginning. And perhaps the most exciting part is that today's discoveries are creating tomorrow's questions. How early did the first globular clusters form? How quickly could massive stellar systems assemble? What role did galaxy mergers play? How efficiently could young galaxies convert gas into stars? And how did these early structures eventually evolve into the galaxies we observe today? Those answers will require more observations, better models, and new generations of telescopes. But the direction is already clear. James Webb has opened a new observational window into cosmic history. It has taken the earliest chapters of the universe from something scientists could mostly model into something they can increasingly observe. The ancient light has been traveling toward Earth for billions of years. Now, after all that time, humanity finally has the technology to read the message hidden inside it. And the deeper Webb looks, the more we discover that the universe's earliest chapters may be far more fascinating than anyone expected.